What if you could shrink yourself smaller than a cell, smaller than an atom, smaller even than a proton? What would you find at the bottom of reality? Would you eventually reach something that cannot be divided anymore? Take a look around. The chair beneath you, the screen in front, the air moving through your lungs, and even your own body. All of it is made of matter. For thousands of years, people have wondered what matter is actually made of. If you keep cutting something into smaller and smaller pieces, does it continue forever? Or is there a final layer of reality? A smallest possible building block that cannot be broken down? Science has given us a remarkable answer. But instead of ending the mystery, that answer opened the door to bigger questions. For a long time, atoms were believed to be the smallest pieces of nature. Then scientists discovered that atoms have an internal structure. Inside them are electrons, protons, and neutrons. And while electrons appear to be fundamental, protons and neutrons are made of even smaller particles called quarks. So what are electrons made of? What are quarks made of? And is anything smaller hiding beneath them? Let's follow the extraordinary journey to the smallest known building blocks of the universe. The first atoms. The search for matter's basic ingredients began more than 2,000 years ago. Around 400 BC, the Greek philosopher Democritus imagined what would happen if you kept breaking an object into smaller and smaller pieces. A rock could become smaller rocks, then grains, then dust. But Democritus believed this process could not continue forever. Eventually, he said, you would reach a particle so small it could no longer be divided. He called these particles atomos, a Greek word meaning uncuttable. It was an impressive idea for its time. Democritus had no microscopes, particle accelerators, or advanced scientific instruments. He was reasoning from simple observation and logic. But there was one major problem. The idea could not be tested. For centuries, atoms remained a philosophical concept rather than a scientific fact. Some thinkers believed matter could be divided endlessly. It wasn't until the early 1800s that atoms returned to the center of scientific discussion. English chemist John Dalton studied how elements combine in chemical reactions. He noticed that substances reacted in consistent numerical ratios. From this evidence, Dalton proposed that matter was made of atoms. Each chemical element contained its own type of atom. Oxygen atoms were different from hydrogen, carbon, or gold. Atoms could combine to form molecules. But atoms themselves were thought to be solid and indivisible. For a while, this model worked extremely well. Then nature delivered another surprise. The electron appears in 1897. British physicist J.J. Thomson was experimenting with electricity inside glass tubes. These were called cathode ray tubes. When electricity passed through the tubes, a mysterious beam traveled from one end to another. Thomson discovered that the beam could be bent by electric and magnetic fields. More importantly, it was made of tiny negative particles. These particles became known as electrons. The discovery was completely revolutionary. If electrons could come out of atoms, then atoms could not be solid, indivisible spheres. They had to contain smaller parts. The atom was no longer the final layer of matter. A few years later, Ernest Rutherford conducted one of the most famous experiments in the history of modern physics. His team fired tiny particles at an extremely thin sheet of gold foil. If atoms were packed solidly throughout, the particles should have bounced back in large numbers. But something surprising happened. Most particles passed straight through the foil. Only a small number were sharply deflected. A few even bounced directly backward. Rutherford realized that an atom is mostly empty space. Almost all its mass and positive charge are concentrated inside an incredibly small central region. This region is called the nucleus. The electrons occupy the surrounding space. Later, scientists identified two major particles inside the nucleus. These were positively charged protons and electrically neutral neutrons. This gave scientists the basic atomic picture we recognize today. An atom contains electrons surrounding a nucleus made of protons and neutrons. But even this picture is only the beginning. Why electrons matter? Electrons are among the most important particles in everyday life. They carry electric current through wires. They help atoms form chemical bonds. They participate in reactions powering our living cells. They make modern technology possible. Smartphones, computers, television screens, and medical devices all depend on the behavior of electrons. Yet an electron is incredibly small. Its mass is about 1,836 times smaller than a proton's mass. So naturally, we have to ask, what is an electron made of? So far, every experiment points toward the same conclusion. Electrons appear to have no internal structure. Scientists have not found smaller particles inside an electron.
An electron does not behave like a tiny container. It is not filled with even smaller objects. Instead, the electron appears to be a fundamental particle. That means it may be one of nature's basic ingredients. This does not prove an electron can never be divided. Science rarely makes claims with absolute certainty. It means that within our best experiments so far, no smaller components have been detected. Particle accelerators have tested electrons at extraordinarily high energies. These experiments examine matter at scales far smaller than an atomic nucleus. So far, electrons continue behaving like point-like particles. They show no measurable internal structure. If electrons are made of something smaller, that hidden structure must exist at a scale beyond anything we have yet observed. But electrons are not the only important atomic particles. Inside protons and neutrons, for decades, scientists thought protons and neutrons might be fundamental particles. That changed during the 1960s. Researchers began conducting high-energy particle experiments. They smashed particles together at tremendous speeds. Then they carefully studied how the particles scattered. The results revealed something unexpected. Protons and neutrons were not simple, indivisible objects. They contained smaller particles inside them. These particles were named quarks. A proton contains 3 quarks altogether. It contains 2 up quarks and 1 down quark. A neutron also contains 3 quarks, but its combination is different. It contains 1 up quark and 2 down quarks. These names may sound playful, but quarks are deeply important. They form the core of nearly all ordinary matter. However, quarks do not simply sit inside protons and neutrons like marbles. They are bound together by the strong nuclear force. This is one of nature's most powerful forces. The particles carrying this force are called gluons. You can think of gluons as messengers of the strong nuclear force. Photons carry the electromagnetic force. Gluons carry the strong force between quarks. They act like a kind of cosmic glue. That is where their name comes from. Without gluons, quarks would not remain bound together. Without quarks, protons and neutrons could not exist. Without protons and neutrons, atomic nuclei could not form. And without atomic nuclei, the familiar universe would disappear. Chemistry would not exist as we know it. Neither would planets, stars, or living organisms. There is an important detail here. The strong force behaves differently from forces we experience every day. When quarks are pulled farther apart, they become even harder to separate. This unusual behavior is called quark confinement. That is why scientists do not normally observe individual quarks moving freely. Instead, quarks remain locked inside larger particles. Are quarks fundamental? Once scientists discovered quarks, a new question immediately followed. Could quarks themselves contain something smaller? At the moment, experiments have found no evidence of internal quark structure. Like electrons, quarks appear to be fundamental particles. The Standard Model treats electrons and quarks as elementary particles. They are not described as being made from smaller ingredients. They are part of nature's basic particle inventory. But fundamental does not necessarily mean absolutely indivisible. History gives a scientist a reason to remain cautious. Ancient thinkers believed atoms were uncuttable. Later, atoms turned out to contain electrons and nuclei. For a while, protons and neutrons appeared fundamental. Then, scientists discovered quarks inside them. So scientists continue testing these ideas. New experiments might one day reveal deeper structure. Or they might confirm that electrons and quarks truly are fundamental. For now, evidence supports the simpler conclusion. Electrons and quarks do not appear to contain anything smaller. The Standard Model, our best current description of fundamental particles and forces, is called the Standard Model. It does not describe matter as being made only of atoms.
Instead, it describes a collection of more basic particles. There are 6 types of quarks. They are called up, down, charm, strange, top, and bottom. There are also 6 types of leptons. The electron is one of them. The other charged leptons are the muon and tau. The remaining 3 are different types of neutrinos. Neutrinos have extremely small masses. They also interact very weakly with ordinary matter. The Standard Model includes force-carrying particles. Photons are associated with electromagnetism. Gluons carry the strong nuclear force. The W and Z bosons are involved in the weak nuclear force. Then there is the famous Higgs boson. Scientists discovered it in 2012. The discovery happened at the Large Hadron Collider. The Higgs boson is connected to the Higgs field. This field helps explain why many fundamental particles have mass. The Standard Model has been remarkably successful. It predicts the results of countless particle experiments. Its predictions often match observations with extraordinary precision. In some cases, the agreement reaches many decimal places. Yet the Standard Model is not a final theory. It does not explain everything in the universe. What physics still cannot explain, the Standard Model does not fully include gravity. Gravity is described extremely well by Einstein's general relativity. But general relativity and quantum physics do not fit together perfectly. This creates major problems under extreme conditions. These conditions include the centers of black holes. They also include the earliest moments of the universe. The Standard Model does not explain dark matter either. Dark matter appears to make up much of the mass inside galaxies. We can detect its gravitational effects. But scientists still do not know what dark matter is made of. Then there is dark energy. Dark energy is connected to the accelerating expansion of the universe. Its true nature remains mysterious. These unanswered questions remind us of an important fact. Even our most successful theories have limits. The smallest answer: so what is everything made of? The world around us is built from atoms. Atoms contain electrons surrounding a nucleus. The nucleus contains protons and neutrons. Protons and neutrons are made of quarks. Gluons hold those quarks tightly together. As far as current evidence shows, electrons and quarks appear to be fundamental particles. They do not seem to contain smaller pieces. But science is not simply a list of permanent answers. It is a process of questioning. It is also a process of testing and refining our ideas. The smallest thing we know today may not be the smallest thing that exists. Every time humanity has looked deeper into nature, another layer of reality has appeared. The universe may be built from a small collection of fundamental particles. But our understanding of reality's deepest level remains unfinished. Here is the memorable takeaway. The universe may have basic building blocks, but we still do not know where the bottom of reality truly lies. Thanks for joining us on this journey through matter. We traveled from atoms to electrons, from protons to neutrons and quarks, and from quarks to the Standard Model. If you enjoyed exploring the hidden structure of matter, hit the like button and subscribe to the channel. Share this video with someone who loves discovering the mysteries of the universe.
If you enjoyed this video, please like, subscribe to Palsa Lab and turn on notifications so you don't miss our latest uploads. At Palsa Lab, we explore space, science, astronomy, AI, and emerging tech, bringing clear explanations and fascinating discoveries. Have a question or idea? Drop it in the comments. Stay curious, keep exploring, and thanks for watching. See you next time.